Let's do some calculations of capacitance series. Let's say we have a capacitance of 6 microfarad and 3 microfarad connected in series between A and B. It's always so. Between 2 points something is connected. So these two are connected in series between A and B. Well, suppose we have a potential difference of 18 volts between A and B. That's the combined potential difference is 18 volt. How does it divide between the two capacitors? That is, what is the potential difference across 6 microfarad capacitor and what is the potential difference across 3 microfarad capacitor? Now, one way of doing it is to calculate the equivalent capacitance and find the charge in the equivalent capacitor. And what do we know about series connection? The equivalent capacitor will have a potential difference equal to sum of the potential difference of the two capacitors, which we said is 18 volt, and the charge in the equivalent capacitor will be same as that of the individual capacitors. So if we find the charge in the equivalent capacitor, we can use it in the individual capacitors case because they have the same charge as the equivalent capacitor. So the equivalent capacitance of these C effective will be C1 C2 by C1 plus C2, which is 6 into 3 by 6 plus 3 in this case. So C effective comes to 2 microfarads. 2 microfarads, and if the potential difference is 18 volt, let's call that V. This V and this V, this is for unit and this V is for potential difference. So let's call this VAB is 18 volt. Now across the 6 microfarad capacitor, the charge on the equivalent capacitor will be what? 2 into 18, 36 microcoulombs. So 36 microcoulomb. C effective is 2 microfarad, 18 volt potential difference, so that's 36 microcoulombs. 36 microcoulomb across this will give us 36 by 6, 6 volt. And 36 across this will give us 36 by 3, 12 volt. So it is 6 volt across this and 12 volt across that. Combined potential 6 plus 12 will of course equal to 18 volt. That's it. This is one way. We don't have to calculate the charge of the capacitor. We're not interested. So you could go with some other logic, like say potential difference in series combination or an inverse ratio of capacitances. We know the combined potential difference. We know the ratio of potential difference. We call this V1 and V2. V1 across this and V2 across this. We know the ratio of V1 by V2, that is C2 by C1, right? Which in this case is 3 by 6, that is half, right? And we know V1 plus V2. V1 plus V2 is 18 volt. 18 volt. So we have to divide this 18 in the ratio 1:2, so 18 into 1 by 3 across first capacitor, that is 6 volt, and 18 into 2 by 3, that's across this. It is 1:2 ratio, right? Inverse ratio of this capacitance will be 3:6, 1:2. So divide 18 in the ratio 1:2, that is 6 and 12. So V1 is 6 volt and V2 is 12 volt. So we haven't calculated the charge here. This is one way of doing the calculation. So one other nice calculation you can do here. Suppose, forget this for a moment. Suppose the breakdown voltage of this capacitor is 10 volt and this also is 10 volt. What is the maximum potential difference you can apply to the series combination without either of them breaking down? Well, for 10 volt potential difference, this can store a maximum charge of 60 microcoulomb, whereas this will be 30 microcoulomb, right? So if this is the maximum potential that this can withstand, the maximum charge it can store is 3 into 10, that is 30 microcoulomb, and the 6 into 10, 60 microcoulomb. Since in the series combination they must have equal charges, so the lesser of the two, 30 microcoulomb, will be the maximum charge the system can store. So 30 microcoulomb and 30 microcoulomb will give us 30 by 6, 5 volt across this, and of course this is 10 volt, 30 by 3, 10 volt. So 5 volt and 10 volt, the maximum potential the series combination can withstand is 15 volt. It is not 10 plus 10, please. It is 15 volt in this case. If it were like equal capacitors, 6 and 6 microfarad, then you could have added up 20 volt, because then each would have the same potential difference. But then if capacitors are unequal, you need to do a calculation. So this is something to learn about series capacitors. Consider this situation. We have 3 capacitors in series between A and B, terminals A and B. This is 6 microfarad, this is 3 microfarad, and this is say 2 microfarad. Now, if the potential difference between A and B, say VAB, let's call that, is say 36 volt, what is the potential difference across individual capacitors? One way of dealing with it is, again, go the same way as we did earlier. What's the equivalent capacitance? Now 6 and 3 in series will give us 6 into 3 by 6 plus 3, that is 2 microfarad. We are replacing these 2 by one capacitor of 2 microfarad. And that equivalent capacitor will be in series with this. 2 microfarad and 2 microfarad will be 1 microfarad. Right, if we have n capacitors of C each in series, equivalent capacity will be C by n. Now, so this equivalent capacitance is 1 microfarad. And that equivalent capacitor will store a charge of 36 microcoulomb. You have learned that equivalent capacitor will store the same charge as any of the individual capacitors. So that's 1 microfarad, 36 volts, so 36 microcoulomb. So this charge, that's the charge in the equivalent capacitor. So this will be 36, same on these capacitors, so 36, 36, 36 microcoulombs. So 36 by 6 is 6 volt. 36 by 3 is 12 volt. 36 by 2 is 18 volt. So 6 volt, 12 volt, 18 volt. Those are the individual potential difference. No serious calculation here. Alternately, you could say if the potential difference classes are V1, V2, V3, so V1 is to V2 is to V3 will be 1 by C1, that is 1 by 6 is to 1 by 3 is to 1 by 2. In series connection, the potential difference will be in the inverse ratio of capacitances and charge will be same. This is what we learned. So this ratio comes to 6 is LCM, so it will be 1 is to 2 is to 3. Now combined potential is VAB is 36 volt, right? So we must divide 36 volt in the ratio of 1 is to 2 is to 3. So 1 part in 6 across 6 microfarad, 1 part in total of 6, right? That's how we should divide that 36 microcoulomb, 36 volt. So V1 will come to 36 into 1 by 6, that is 6 volt. And V2 will come to 36 into 2 by 6, that is 12 volts. And V3, that is 3 parts in 6, 3 parts in 6, so that will be 18 volt. We have not calculated the charge here, so you could do this way. If you are interested only in the potential difference across individual capacitors, it's good to know that potential differences are in the inverse ratio of capacitances in series combination. The other thing we used was that charge in the equivalent capacitance is same as the charge in any one of the individual capacitors. So this equivalent capacitance came to 1 microfarad, since applied potential is 36 volt. Equivalent capacitor will store 36 microcoulomb of charge. So 36 by 6, 6 volt, 36 by 3, 12 volt, 36 by 2, 18 volt. Done. Either way, I think you can prefer this in case you want to do a quick calculation. You don't have to calculate the charge on the equivalent capacitor. Consider this situation. 3 capacitors are in series. So the breakdown voltage of this capacitor V1 max, say, is 10 volt. And say this V2, second one, V2 max is say 12 volt. And this one, V3 max, is say 4 volt. Now the question is, what is the maximum potential difference across that can be applied to the series combination? And you can see that this can store a maximum of 60 microcoulomb of charge, and this 36 microcoulomb of charge, and this 8 microcoulomb of charge. Now, in series combination, charge must be same on all the three of them. So the minimum of the maximum charges that these capacitors can store. This can store maximum of 60, maximum of 36, maximum of 8. So 8 microcoulomb charge is what you can store on the equivalent capacitor. Sorry, yes, 8 microcoulombs is charge you can store in any one of the capacitors, because if it's more than 8, this will break down. So the others can store more charge. So we are not interested in the ones which can store more charge. The least of the maximas. This is the maximum charge you can store is 60 microcoulomb. This is 36, and this is 8. Say microcoulomb. So 8 maximum is 8 microcoulomb, right? So that will give us a potential difference of the combination B between A and B is across this 8 microcoulombs by 6 microfarad, 8 by 6 volt, plus this will be 8 by 3, and this will be 8 by 2, that's 4 volt of course. So you can take the LCM and work this out. This will be 6, right? LCM is 6. 8 plus, this is 16, and this is 12. Right? So this will give us, 24 plus 36 by 6. This is 6 volt. The maximum potential which can apply to this combination is 6 volt. Yeah, that's it. Even if they were all able to withstand equal potential difference, say 10, 10, 10 each, you are not going to add them as 10 plus 10 plus 10 and say the system can withstand 30 volt. Even then you should do a calculation like this. Same situation as earlier, but now we are saying each of them can withstand same 10 volt. And the maximum potentials that you can apply to the combination is not sum of these three. You do the calculation the same way as earlier. This can store a maximum of 60 microcoulomb. This can store a maximum of 30 microcoulomb. This can store a maximum of 20 microcoulomb. So least of the maximas is 20 microcoulomb. So you can store a maximum of 20 microcoulombs on this combination. Then what is the potentials that between A and B that you can apply across this? We said it is 20 microcoulomb by 6 microfarad, and this is 20 microcoulomb by 3 microfarad, and this is 20 microcoulomb by 2 microfarad. So work this out and you will get what you want. This will be 620 plus this is 40 plus this is 60. That will be 120 by 6. So this is 20 volt. The maximum potential across this combination can be only 20 volt, not the sum of these three 30 volt. So breakdown potential for the combination, you should do a calculation like this.